As you watch the waves, you realize it has such a simple, formally simple motion, but realize there's something actually very complicated inside. The question is, how do these simple motions come from these complicated interactions? One of the things that we are interested in is to find patterns within randomness. I usually like to walk close to water, close to the river, the lake, or the forest areas that is close to nature. I tend to be relaxed, and that makes the chance higher to have some real good ideas. I had dreams about math. Sometimes I dream about questions that I actually haven't worked on. I had these dreams when I was writing these papers about legitimate math questions, but in reality I haven't written any of the papers. I'm a professor of mathematics at the University of Chicago. I mainly work in the field of PDEs, partial differential equations, and also in connection with probability. The questions I work on mainly concerns how do you see these real-world phenomena like fluid, like waves, from microscopic pictures of interacting tiny particles. I grew up in Shenzhen in China. When I was in 6th grade, I was working with my dad on a particular question about finding patterns in a particular sequence, and I remember we spent like a few hours together to solve that, and at the end we were really happy that we could solve this question, and that was perhaps the earliest thing I could remember when I get excited about mathematics. I started learning Go when I was maybe about 6. The game of Go is really about analyzing the positions of the board and really having an accurate idea about it before you make your move. In some sense, it was maybe closer to the idea of thinking about mathematical questions and having an idea of the question before you start really working on it. I seriously played it for a few years. I even thought of going for professionals, but in the end I wasn't successful, so I gave up and I turned to the math competitions. I went to the IMO in Slovenia in 2006 and got a gold medal. I started to think maybe I really have some talent in this field and maybe I should really try to pursue this field. Consider a billiard ball. It moves in a straight line, collides with other billiard balls, changing velocity, and keeps moving. Simple. But what if we have trillions of such tiny balls constantly colliding with each other? This is what happens in the hard sphere model of gases, where the little billiards are the gas particles. For such a huge system, it's practically impossible to track each individual particle precisely. Instead, we're interested in the statistical information of the system, overall distribution of the particles, average velocity, and so on. This will be captured in a single density function, which is governed by Boltzmann's kinetic equation. In the parallel picture, consider water waves, which can be viewed as a system of magnetic wave packets, again constantly interacting with each other. This occurs in the physical phenomena of wave turbulence, where the statistical information is governed by the wave kinetic equation. With collaborators, we've successfully justified both scenarios in suitable kinetic limits on mathematical level. The key challenge is that an average particle will experience arbitrarily many collisions and complicated dynamics, as opposed to less than one collision in previous works. To overcome this, we introduced multi-layer diagrams representing the whole collision process and inventing ways to analyze them effectively. These diagrams are enormous in size, but they are formed by the basic building blocks. Each of these basic scenarios, for example, when the billiard ball has one single collision, or when it has one collision that causes a second collision, is easy to estimate. Then, by a carefully designed cutting algorithm, we can break any diagram into such building blocks, which in the end guarantees a complete understanding of the diagrams and leads to the resolution of the full problem. after several thousand years, there's still a lot of mysteries about the universe. Our understanding of the physical universe on mathematical level is still extremely small. The thing that keeps me in this field is the happiness when your plan works perfectly, that you are able to solve the questions you are faced with.